Welcome! Today we're going to tear apart the very idea of sound. We're going to look under the hood of everything from a beautiful melody to just plain old static and figure out what makes them tick, what gives them their unique character. Let's get into it.
All right, let's start with a question that I think we've all wondered about. You hit a middle C on a piano, and then you play that exact same note on a guitar. You know instinctively that they sound completely different. But why? I mean, what's actually going on there physically?
Well, to get to the bottom of that, we have to forget about those perfect, clean sine waves you see in science textbooks. See, most of the sounds we hear in the real world, especially music, are what we call complex tones. And the amazing thing is, they're hiding a really beautiful, hidden order.
So what is a complex tone? The key word here is periodic. That means that even if the sound wave has this really wild, complicated shape, that exact same shape repeats itself perfectly over and over and over again. It's like a stamp. And that repetition, that's what our brain hears as a musical note.
Just take a look at these. I mean, they couldn't look more different, right? One's got these sharp spikes, the other one looks like the teeth of a saw. But look closer. You can clearly see that there's a pattern, a little chunk of the wave that just repeats again and again. That's what we're talking about. That's what makes them periodic.
So the next obvious question is, how fast is that pattern repeating? Well, that speed is what we call the fundamental frequency. And here's the cool part. That is exactly what we perceive as pitch. So when you hear a high note, it just means that complex pattern is repeating really, really fast. A low note, it's repeating much more slowly. Simple as that.
Okay, but where do these wacky, complex shapes even come from? It turns out they're actually built from some incredibly simple ingredients. And once you understand this, we're going to finally be able to answer that guitar versus piano question.
Believe it or not, every one of those complicated waves is really just a bunch of simple, pure sine waves all added together. We call these harmonics, and you can think of them like ingredients in a sonic recipe. The best part is they aren't just random frequencies. They're always in this perfect mathematical relationship, whole number multiples of that main note, that fundamental frequency.
We can actually build one right now. So you start with your main ingredient, the bass note, which is the fundamental. Then you start layering on top of it. You add a pure tone that's exactly twice the frequency. That's your second harmonic. Then another one at 3 times the frequency and another at 4 times. And as you add them, they all blend together into this one new complex shape.
And this image just illustrates it perfectly. Look, you can see the 4 simple ingredients at the top, and when you mix them all together, boom, you get the final complex wave down at the bottom. That graph on the right, the spectrum, that's basically the recipe card. It tells you exactly which harmonics you used and how much of each one is in the final mix.
And all of this brings us to a really important word, timbre. You pronounce it timbre. And it's just a fancy way of talking about the sound's unique character, its fingerprint, its color. So the reason the guitar and the piano sound different playing the same note, they have a different timbre.
This slide nails it. Check it out. Both of these sounds have the exact same pitch, a fundamental frequency of 200 Hz. But their harmonic recipes are completely different. The sound on top has a lot of strong lower harmonics, which makes it sound kind of warm. The one on the bottom, though, has stronger high harmonics, making it sound bright. See? Same note, different recipe, totally different sound. That, right there, is timbre.
Okay, so we've been talking all about this beautiful mathematical order inside musical sounds. Now, we're going to flip the script completely. Let's talk about the exact opposite, the sound of pure, total randomness, what we call noise.
So here's the big difference, right? A complex tone is periodic. It's got that predictable repeating pattern. Its frequency recipe is made of these nice, neat little spikes, the harmonics. Noise, on the other hand, is aperiodic. There's no pattern, none. It is totally random and unpredictable from one second to the next. It's chaos.
I mean, just look at the waveform for white noise. It's a mess. There is no cycle, no pattern you can possibly trace. And if you look at its spectrum, it's not a few clean lines, it's just a continuous smear, a mishmash of pretty much all the frequencies at once.
But this is where things get really, really weird. It turns out that the frequency recipe for this continuous, random hiss, what we're calling white noise, is almost identical to the recipe for a super sharp, instantaneous click. I'm not kidding. They're both made of the same flat, continuous spread of frequencies.
So wait a minute. If a long, drawn-out hiss and a short, sharp click are made of the exact same frequency ingredients, what are we missing? Why on earth does one sound like shh
and the other just sounds like a pop.
The secret, it turns out, isn't what frequencies you use in the recipe, it's how you line them up. It all comes down to their timing, a property that scientists call phase.
This is the magic trick right here. To make a sharp click, you take all those frequencies and you make them peak at the exact same instant. It's like a whole crowd of people shouting now, all at once. They add up to create one giant, super brief spike. But for noise, you use the same frequencies, but their timing, their phase, is totally random. It's like that same crowd shouting whenever they feel like it, creating a constant, jumbled, chaotic roar.
So wow, we've gone all the way from the perfect, organized structure of music to the absolute random chaos of noise. And we found out that sometimes the only thing separating them is something as subtle as timing.
All right, let's just recap the big ideas. Musical sounds, these complex tones, get their pitch from how fast their pattern repeats. They get their unique personality, their timbre, from the specific recipe of harmonics. Noise, on the other hand, is the total opposite. It's random, aperiodic. And that final mind-bending piece of the puzzle, the difference between a hiss and a click, isn't the frequencies themselves, but their phase, their time.
So think about that for a second. The hum of your computer, the sound of a voice, the wind in the trees. Every single sound you're hearing right now is its own unique story. It's a story written in frequency, timbre, and phase. A constant dance between perfect order and total chaos. Now that you know that, what are you going to listen for next?